Starting with topic 2.2, separating and purifying substances. Now, in case of separating and purifying substances, uh, there are many methods. On the very next page, page number 28, you'll find a table on the top left corner of the page, and you'll see for different types of mixtures, we have many different methods. You'll see there is some about 8 to 9 different names over here. So exactly how would we know that which kind of separation technique are we interested in? So we have this pink portion that actually helps us to think and decide which separation technique is going to be the best one for us. For any particular mixture, number one, it depends upon the type of the mixture. And number two, it depends upon the substance in the mixture we are most interested in. All right. So in order to understand these both points, I'm going to take examples from the same table. So let's move on to page number 28. In this very topic, 2.2 will be going in back and forth on the pages and the diagrams to correlate the work. So starting off with this table, on the top, you'd find solid plus solid powdered mixtures. Now, there are many powdered mixtures for us around the world that we use daily. In case of their method of separation, if it's a powdered mixture, it's really difficult to separate one powder from the other. So what do we use? We use different in their different properties. For example, they might have a different density, they might have a different solubility. One or two out of them might sublime, the others do not. And then the magnetism. Now, we can also go for suspension of a solid in a liquid that can be separated in terms of filtration or centrifugation processes. We're going to discuss the details of these processes later, also what their names mean or how do we carry out these processes. Next one is liquid plus liquid immiscible. Now you understand what the word immiscible means. That means the two liquids we're talking up top are not soluble into one another. They cannot dissolve into one another. So we can use a separating funnel, or we can use another process by the name of decantation. Solution of solids and liquids. Now, this is one of the most common kind of solutions that we come forth with. For example, the mixture of sugar in water or salt in water is the solution of solid in liquid. Now, it really depends upon what do we need by the end of the process. So if we require the solid, for example, in this case, they're mentioning if we require the solid, we either use the process of evaporation or better yet, call it the process of crystallization. In order to obtain the liquid, we use the distillation. So if the mixture is of sugar and water, then if we require the sugar, we're going to use the evaporation or crystallization technique. If we require water, we're going to use distillation technique. Most of the time, I ask my students not to use just the word distillation. Instead, change this by using the word simple distillation so that you can differentiate between this kind of distillation and the next one in the very next box. Moving on to that, two or more liquids mixed together if they are miscible. Remember, we studied immiscible liquids. Now is the time we study miscible liquids. They are separated by another kind of distillation, that is fractional distillation. Now, solution of two or more solids in a liquid's chromatography. For example, think of adding some salt and some sugar at the same time in water. If you need the solid separate, then you can't use any of these processes listed over here. You can only use chromatography in order to get those materials separate. So let's go through by these processes in the order that they are given in the book, right? This table was just for introduction, so you might still have many questions from the table. Let's clarify them by using the information. I just jumped to the previous page, page number 27, since on this page, you'll find the very definition or explanation for decanting. Now, if the solid is insoluble from a liquid, just like we gave the example of sand in water, sand is insoluble in water. What we can do is that we can go with decanting. What is decanting? If the particles of solid are large enough, they settle down at the bottom. Once the solid has settled down to the bottom, the liquid can be carefully poured off, and this process is known as decanting. Even decanting itself is defined in the same way. careful pouring, right? So do you understand the point?
Yes, sir.
Now, let's draw a simple diagram. We have a beaker, we fill it with water, we throw some sand, which would all settle down at the bottom. All you need to do is to tilt the beaker, right? Tilt it like this so that the water comes out of it, and make sure you just take this much of water. You tilt the beaker and take this much of water out, leave this water and sand with it. So doing that will leave us with most of the sand and a very little amount of water. So decanting is not a very good process when it comes to that, since you were never able to get the whole amount of the substance you were interested in. You were interested in taking out water, but you were never able to take out all of the water. Make sense?
Yes, sir.
So you're not going to prefer decanting unless you don't have any other process to follow. Moving on the next page, right below the table, let's start with filtration. Now, in order to separate solids from liquids, filtration is a very good technique. In this case, we can separate an insoluble material as residue on the filter paper. Filtration is useful because both phases can be obtained in one process, which means if you have a whole filtration setup like this one, let's go through the parts. This one is a stand. We commonly call it retort stand. All right. You may also call it stand with clamp. Since you can see a clamp over here, because of which we are able to set it up like this. All right. So what do?
Okay,
We
sir.
put a filter funnel, we put a filter paper in it, and we properly fold the filter paper so that covers the bottom part of the filter funnel. Just make sure you don't pierce a hole in the filter paper, otherwise the whole purpose of the filtration dies. We also call it support. This part is known as support. And then the solid that remains on the top of the filter is known as residue. Why is the solid not able to pass? The particles are big enough not to pass through the small pores present in the filter paper. The liquid that comes through is known as filtrate. So we have particular names for this one and this one. Make sure you use the same terminologies whenever and wherever required, right?
Sir, can you repeat what is residue?
Residue is the solid that wasn't able to pass through the filter paper. Okay, the filter paper is something that has very small pores in it. These small pores act like small holes. It's easier for water to pass through these holes since the particle of water is very small in size. As compared to sand, sand has larger particles, so the larger particles will not be able to pass through the small pores or holes present in the filter paper, so it would stay on the top of the filter paper. And whatever solid that we get, we have a generic name for it, and that generic name is known as residue. Residue is usually the solid that is left over on the top of the filter paper since it cannot pass through. Make sense?
Yes, sir. Thank you.
Okay, good. So the liquid usually passes through, and if it was a case with water, water would easily pass through the filter paper. Anything that is soluble in water will also be able to pass through the filter paper. Anything insoluble will not be able to pass through. For example, let me clarify. Let's say if you have a little amount of sand and a little amount of salt, and that those both of them are present in water, and you pour it through over here, then you would definitely get some water over here. Plus, that water will also contain the salt, since the table salt that we uh, have been talking about is a common salt example, is soluble in water. It can pass through. Since water can pass through, it can pass through too, right? So the sand would stop
Yes,
over here. So what would be the residue? The residue would be just sand. What would be the filtrate? The filtrate would be both water and salt. I hope this example clarifies everything, right? Does it?
yes, sir. It's
Good,
clear.
good. Now, let's get to back to the same paragraph we were at, and we're gonna define or explain the other part of the diagram as well. Now, filtration is very useful. Both of the phases can be obtained in one process. We had sand in one part and the water on the other. The liquid phase is known as the filtrate. The process can be speeded up by using a vacuum pump to suck the liquid through the filter paper, and that's commonly known as a Buchanan's funnel. Buchanan's funnel and flask is actually shown in that B part of the diagram. Now you'd notice that a Buchanan's funnel is different from a filter funnel. Buchanan's funnel has a perforated blade, and when I use the word perforated, it means it has small holes in it. Perforation means holes. It also acts like a filter paper. All right. We sometimes also cover it with the circles of filter paper. Then we fill it up with the liquid. The filtrate passes through. There is a vacuum pump that is connected through the side arm. It actually sucks in the air, which pressurizes this water to pass through it with a speedy flow. Now, when we come to this diagram and we say that the presence of Buchanan's funnel and a vacuum pump in this whole diagram can actually speed up the process, which brings us to a point that filtration might be an easy process. Filtration might be something that you might have easily done with your own hands in the very first time successfully. But that doesn't mean there is no downside to this process, sorry. So what's the downside to this process? Let me tell you, though, one of the only downsides of this process is that it's slow. So in order to speed it up, what do? We use a Buchanan's funnel. All right?
Okay, sir.
Good, good. So now you know the good side of filtration and as well as the bad side. The good side is we get both the phases in a single process. There are other good sides as well. For example, it's very easy to perform. There is not whole big of a learning curve there. Even students can perform it in their very first time successfully. Now, the materials that we have used, the stand, this filter paper, this filter funnel, the beaker, they are one of the most inexpensive materials on the planet. They are easily available. So yeah, these are some good sides. But the downside was it is slow. So what do we do? We use a Buchanan's funnel along with the whole set of apparatus and a vacuum pump to make sure that the process becomes a little bit speedier. So various large-scale filtration methods are used in the industry. The most important one that we consider are the filter beds that actually treat water for household use, the ones that you have discussed in the previous chapter, chapter number 1. Now, another method of separation of an insoluble solid from a liquid is centrifugation, where the mixture is spun at high speeds in a centrifuge. This causes the solid to be deposited at the bottom of the centrifuge tube, and the liquid can be carefully decanted off. Now, centrifugation is a process which has been rarely used in the past papers, past 10-year papers. If you pick them up, you'll hardly find a single question about centrifugation. But still, we do explain the main lines so that if this comes as a process this time, this year as a question, you'd know how to solve it. So do you know any real life application to centrifugation? Okay, let's not waste time. I'm going to write a name and I'm going to ask you, as soon as you read the name, do you know how that works?
Yes, I know
Okay.
how washing machine works.
Good, good, great. And that's a very great example of centrifugation. Let's see if we have a top load, not at a front load. There is a motor at the bottom of the washing machine. What do? We fill it up with some of the water. We throw in some dirty clothes. We put in some washing powders, the detergents, the softeners, that kind of chemicals. And what do? We turn it on. As soon as we turn it on, this motor starts rotating. So what happens is that the whole water flows in circles, spun at high speed. The machine itself is known as a centrifuge. What happens to this mixture? The solid is deposited at the bottom. So whatever dirt or dust or solid pieces that we have, they slowly, because of this circulation movement or spinning, settle down at the bottom. The dirty water along with the clothes remain up top. Since they're lighter, the dust was heavier. So what do? After some time, when the spinning is complete, we take clothes out of it, we wash them again, we dry them, there you go. They're clean again. Good as new, right?
Yes, sir.
Good. The liquid can be carefully decanted off. You may decant off the liquid. Since that's wastewater, we simply waste it out. So moving on, the next category, separating immiscible liquids, liquids that do not dissolve in one another. The technique that we used was separating funnel. So how are we going to use it? Let's move on to page number 29 and let's do it with the help of a diagram. Now you see a diagram in front of you which has two parts, A and B. The A part gives you a separation funnel drawn and some steps written in front of you. The B part gives you an actual diagram with oil and water in it, right? And you'd notice that in both the diagrams, you have two liquids. Since they're not dissolvable into one another, so what you would see is that one liquid as a separate layer and the next one as a different layer. Even in a real example, you'll find water at the bottom with its colorless structure and oil up top with its oily yellowish appearance, right? Now, I want to tell you a few things that are related to your previous classes, maybe class 7 or 8, and which is also considered as a prerequisite by the examiners in IGCSE. As soon as you try to add two immiscible liquids, they form two different layers. The bottom layer of this whole process usually composes of a more dense liquid. And the layer up top is less dense usually. As soon as you see any layers, you are going to quickly assume about their densities. The one at the extreme bottom would be the most dense, the one at the extreme top would be the least dense, and anything in between can be compared from their top and bottom positions. I hope that clears out the density part.
Yes, sir. It's clear.
Good, good. Now, talking about the process and how we're going to proceed with the process, let's study the points in diagram part A. Now, the mixture of immiscible liquids settles into two layers as the liquids do not mix. Even if sometimes the layers come into one another and join one another, let it stand for some time. If you let it stand for 15 to 20 minutes, and if you don't touch it, if you don't stir it, if you don't shake it, it would again form two separate layers as shown in the diagram. What do then? We slowly open the tap carefully so that we only let the bottom layer run into a beaker. What do? The tap is closed, the beaker is changed, the tap is open to let the top layer run out. And that's how we have two separate layers. But that's not exactly the way I tell my students to perform the experiment. What I tell them to is to perform it a little bit differently. So we're going to go with the same steps, but I'm going to make a small change in them. Okay, what you're supposed to do is to take beaker number 1 first. Open up the tap. Of course, the most dense layer or layer number 2 over here would move into the beaker since it's more dense and it's present at the bottom. As soon as you see this bifurcation of both layers moving, this is going to move all the way closer to the tap. As soon as it gets extremely close to the tap, close the tap. Change the beaker. Now you have solution 2 in the first beaker. Now put another new dry beaker. Open the tap carefully and I'm going to raise these parts. And I'm going to call this solution 2. And just this time, a little bit of solution 2 and a little bit of solution 1. Let both of them run into the next beaker. So in the next beaker, you would have a very less solution 1 plus 2, and that in a very small amount, since you only had the middle portion of both the layers run into this beaker. That's easy. Close the tap, put a new dry beaker, and take out all of solution 1, fill it up. There you go. You have done it in like this. By doing it like this, you'd have pure 1 over here, pure 2 over here, but some amount of 1 and 2 over here, which was the middle layer. How are you going to separate that? Use this beaker, and this time use a slightly thinner, something with a less diameter, and same separating funnel with the tap at bottom, right? So you use the thicker separating funnel in the first go, use a thinner one in the second go. If needed, use a more thinner one in the third go, so on and so forth. In about 2 to 3 times, you would be able to completely separate drop by drop with patience the whole liquid 1 in one beaker and liquid 2 in the other one. Make sense?
Yes, sir.
So instead of what's written over here, if you do it my way, it would be easier and you would have a much accurate solution having pure quantities of both liquid 1 and liquid 2. So if this is clear, let's get back to the previous page and see what we had next. Now, the lower denser layer is then tapped off, and we can also tap off the upper layer afterwards. We're done with the first one. So there is another example in chapter number 9, blast furnace, molten slag and liquid iron are tapped off separately since they are immiscible and they form 2 separate layers. So this process can be carried out with any kind of immiscible liquids. If they do not react with one another, if they do not dissolve in one another, we can always separate them with an easier method like separating funnel. Moving on, separating mixtures of solids. Now, when you're going to separate mixtures of solids, I hope you understand we discussed some differences in properties. There were 4 properties that were named over here: density, solubility, sublimation, magnetism. So we're going to start with different properties up next. The first property in the list is density. For example, panning for gold is still carried out in the search of new deposits. Now, let's go a little bit into history. Amazon River, a big river in South America, was always attracted by the people because when they used to pan out for the dust present at the seabed, they usually get very small particles of gold. What usually families living nearby used to do is that they get up early in the morning, everyone would pick up their own pan, the males, the females, even the children. They went to the river nearby, they started panning it, they panned for the whole day. At the end of the day, they would be able to collect a little bit amount of gold, and they used to sell that gold to the merchants nearby in order to earn their bread and butter. I hope when I use the word pan, you'll understand it is something like this, which actually has a mesh of net, iron net like this in it at the bottom. So when you try to move it in up and down or left and right positions, the water will leak out of it since there are holes at the bottom, and some dust or the gold particles will stay on top of it, right?
Yes, sir.
Mechanical sifting is also the same thing, almost, although that's done with the help of machines in a much larger scale, but we used to do the same thing. I hope you're familiar that the pan-like structure I'm talking about, a similar structure, but a smaller one, is the one that we commonly use at homes. I hope you might have seen it or used it yourself. We call it a strainer, and we actually strain tea powder out of our teas before we start drinking or taking that tea. And I hope you have seen the process with your own eyes, right?
Yes, sir.
Then panning is much similar to that one. Okay. Mechanical sifting, or simply talking about sifting, is the same process.
Okay,
Okay,
sir.
moving on. Magnetic properties. As soon as I use the word magnet, I hope you understand that this is something which can attract specific metals. When I use the word metals, magnet attract only three metals, which you need to be confirmed about, which are not written over here. So most of the time I ask my students to write the magnetic materials. Magnets can attract or repel only three metals with a stronger force. The rest of the metals are attracted or repelled with a very weak force. So iron, cobalt, and nickel are magnetic materials. They are easily and strongly attracted by a magnet. So what do? We use magnets to clean or to dig or to separate these three metals from the rest of the stuff that is not attracted by a magnet. How do we do it? It's pretty easy. It's environmentally and economically important that we use the same process because it's pretty good in case of recycling of materials. Iron objects can be picked out from the scrap metal using electromagnets. And when I use the word electromagnets, I hope you're clear with the word from physics. Are you?
Yes, sir.
I hope you understand that there are big pieces of metallic iron and we have some copper coil wrapped around it. And as soon as we connect this coil to a battery and turn on a battery with a huge voltage, it quickly turns this piece of iron into an electromagnet. Hence the name electromagnet, magnet formed with the help of electricity. Bigger magnets, almost the size of a car, are used in junkyards and all around the world to pick up scrap metal from the heaps of rubbish so that we can recycle those metals. Fair enough?
Yes, sir.
Moving on, the next property is solubility. When I talk about solubility and a difference in solubility, the process is actually named a little bit differently, and the process it is usually taken in steps. But book over here tries to explain the same set of process in the form of a paragraph. So what I usually do for the ease of my students, I ask them to write notes over here. So if you have your book ready along with a pencil, you should write a little bit of stuff at the bottom of page number 29 for your own ease. You ready?
Yes, sir.
The process in differences in solubility is commonly known as crystallization. All right. And crystallization is usually performed in four steps. The first step is formation of a saturated solution. Now, when I use these words, I hope you're clear about the types of solutions. You understand when I use the word soluble, insoluble, miscible, immiscible, saturated, unsaturated solution. Do you get the point when I say it out loud like this?
Yes, sir.
Good. So what we can do is that we can take an example of sand plus salt powdered mixture. Now, sand plus salt, if they are a powdered mixture, it's very difficult to separate them. Salt is something that we eat every day. Sand is something that is insoluble and should not never be consumed by humans. If we try to consume sand, that actually causes many issues in the body. Among the top of those would be indigestion and formation of a kidney stone. So what do? We need to purify the salt that we use every day. And when you're going to go to your dining table to pick up the bottle of salt over there, or you're going to go to the kitchen, you'd find pure white salt over there. You won't even find a single grain of sand in there. So that's the separation, that's the kind of separation we require. Crystallization can make it happen. What do you need to do? If you have some sand and salt in a powdered mixture, and if you want to separate it so much so that you can get pure crystals of white salt and no grain of sand with it, you can start by forming a saturated solution of salt and sand in water. How would you know you're going to add it to water? It's mentioned over here. A suitable liquid solvent is added. I ask my students to uh, make sure that you understand the word suitable over here has a condition, and that condition is mentioned in the very next line. The solvent must be able to dissolve one of the solid substances, but not the other. So why did we choose water? We knew that if we choose water, salt will form a soluble solution and sand will form an insoluble solution at the same time, which means the salts will get dissolved in the same water where sand will sit at the bottom. That's the condition for the suitability of the liquid. So if you don't have water, if you can't use water, any other solvent would be suitable if and only if it dissolves one of these things and does not dissolve the other one. Make sense?
Yes, sir.
Good. Which takes us to our step 2. As soon as you're done with it, filter the solution. So the next step is filtration. Now you very well know that if sand is insoluble, it's going to stop on the filter paper, and if the salt is soluble, it's going to move along with the water all the way to the filtrate. So what happens, this insoluble material becomes the residue of the filter paper, and the soluble material becomes the filtrate of the filter paper. Clear enough?
Sir, the insoluble solution will become the residue and the soluble substance will become the filtrate, right?
The insoluble substance will become the residue. The soluble solution will become the filtrate. What's the
Okay,
difference
sir.
of what you said and I said is we only get one substance as a residue, but we get an entire salt solution, which means salt along with water as filtrate. Why? Both salt and water were able to pass through the filter paper, hence they are a filtrate, hence the word solution. Sand alone was not able to pass the filter paper, so it would stay alone in the form of the compound on the top of the filter paper known as residue. So the insoluble material will stop in the top of the filter paper in the form of the residue. The soluble solution, which means both the salt and the water, will pass the filter paper to become the filtrate at the bottom. Clear enough?
Yes, sir.
Good. This brings us to our third step. The third step is evaporation. Remember, evaporation is done for the filtrate. All right. Which means what are you going to do? You're going to evaporate the water so that you can get the pure crystals of the salt. But evaporation, let me tell you, is not the last stage. Since by the end of the evaporation, before it is just complete, the water and the salt will become really jumpy. You cannot keep heating it. Otherwise, the salt might jump all the way from the evaporating dish onto you. So what do? We evaporate most of the water, but not all of the water. And we stop heating it, which brings us to the fourth step, in which as soon as we stop heating comes the step of drying. Since the solution with little amount of water and most amount of salt is left, it's so hot that even if we leave it there, even if we let it stand, the water would automatically evaporate, just leaving the salt behind. So the last step, drying, is also known as the main step or the naming step as crystallization. You may write crystallization as the last part of the step itself, but I encourage my students on using the word drying instead of crystallization. But both words can be used. Why? It's a matter of perception. If you let the water dry, that's because we can call the whole process as drying. If you let the water dry, what do we get at the end? We get pure crystals of the salt. Hence, the process is also known as crystallization. So it's just a matter of perspective. Make sense?
Okay, sir. Yes.
Which means you can use both the words as the last or final step. You are going to go with 4 steps only in the case if the examiner asks you to get the pure crystals of the salt. We have seen exams, and very rare at that. Sometimes the examiner asks you to get the sand. Then you do not need to go with these 2 processes. The sand was separated at this point. So what would be the next process? The next process would be the drying of the filter paper. And that's about it. If you require sand, you just need to go up till the filtration process, dry the filter paper so that you don't get wet sand, you get dry sand. If you're interested in the salt, go with all 4 steps so that you can get pure white crystals of salt after the drying is complete. Right?
Yes, sir.
Which brings me to my next point. And I explain it at this point so that is easier for the student to understand. Drying can be carried out by 3 different ways. First of all, under a fan, which is one of the easiest ways. Put up whatever you want to dry. Let's suppose if you want to dry your filter paper that consists of sand up top, no problem. Pick out the filter paper, put it under the fan will dry it in some time. You can also dry it under the sun. Since under the sun there would be more heat and the drying process can be made faster. But we do not usually recommend drying under the sun because the substance might react under the sun. All right. So we stick to a safer process, drying under the fan. The third and last process is to use an oven. Just like we have ovens at home, we also have ovens in the lab. And we can actually go for a very speedy drying process if we dry it in an oven. All right. So now you know all 3 methods of drying. If you are asked to consider the drawing method, you may write any of them in the exam. Clear enough?
Sir, लेकिन जो machines में dryer होता है, what about that?
I didn't get the whole question. I did get the first part. जो machines में dry होता है वो. What was the rest of it?
What about it? I mean, can we use that?
Which machines are you talking about? Are you talking about the drying machines we commonly use after washing our clothes at homes? Are you talking about some other machine present in the lab? Which one?
No, the home one.
Oh, those are
The washing
spinners.
machine.
No, the dryers, well, the most of them are spin dryers, and they actually have the very similar model as compared to a washing machine or as compared to a centrifuge before. They spin the clothes, the wet clothes. If you spin the wet clothes, the water will come out of it in fine, small droplets. They spin it at such high speeds that when the clothes spin, the water is given out in the form of droplets to all the sides. That water is collected at the bottom as a waste bin and is usually wasted after. You get a cloth with very little amount of water on it, so you can easily spread the cloth anywhere in your home and it would dry up too quickly. Even more quicker than any other process of it, like drying it under a fan or drying it under the sun, which are the two most common types of dryings for the clothes around the world. Make sense?
Okay, sir. Yes.
Good. So this completes the crystallization process. Let me tell you, a diagram related to crystallization process is given on the top of page number 30. This shows how we use the evaporating basin and how we evaporate the water at the third step. All right. Some points of this crystallization process are also written over here, and the slow cooling or filtration and drying is also mentioned over here. So I mentioned all of the stuffs at one place in the form of points, so it's easier to remember for the students. If you're clear with the differences in solubility or the crystallization process, can we move on?
Yes, sir.
Next one is separation based on sublimation. There are very little amount of solids that can sublime as compared to the ones that can melt or boil, right? So what can we do? We can actually use the process of sublimation as a separation technique. But in order to apply that technique, there is a prerequisite. One of the substances in the mixture are supposed to be able to sublime. Take a look at this mixture. This mixture is composed of ammonium chloride, the formula for which is NH4Cl, and sodium chloride, the formula for which is NaCl. Sodium chloride is the basic salt that we eat every day. Ammonium chloride, however, is different. If you remember, this is the compound that I gave the example of on the very first pages of this chapter as the compound that can sublime along with carbon dioxide and iodine. Do you remember the example?
Yes, sir.
Good. Then you'd know that out of this mixture, ammonium chloride will sublime and sodium chloride will not sublime. So what do? We put that mixture into a boiling tube. A boiling tube is bigger than a test tube. Take a look. This is a boiling tube, and a boiling tube is thicker, so much so we are able to put a test tube inside a boiling tube, right? The test tube has an arm in which cold water goes out, and then there is a delivery pipe up top in which cold water comes in. We have mixture of ammonium and sodium chloride present at the bottom, which we keep heating. Ammonium chloride sublimes. After it sublimes, the gas particles rise up, and those gas particles, after they rise up, they actually stick to this test tube over here. As you can see the dots over here, this is the compound that sublimed. Why did the compound sublimed and converted back from gas to solid and stick over here? Is because we have cold water running in through this entire system. So as soon as this hot gas comes in contact with this cold water tube, the heat is exchanged, the gas becomes cold, and it sticks to the whole thing over here. It sticks to the bottom of the test tube over here due to the heat exchange, right? Make sense?
Yes, sir.
So the ammonium chloride sticks to the bottom of the test tube. We can, at the end of the experiment, take the test tube out, scratch off the compound that was adhering to this piece of apparatus or bottom of this test tube, and there you go. You get your ammonium chloride separated from the sodium chloride. Good enough?
Yes, sir.
Good. We're done with many techniques, and moving on, let me clear everything up. You'd find simple distillation and fractional distillation on these pages, and then chromatography on this side of it. Unfortunately, the heading for paper chromatography is missing over here at the bottom of page number 31, and that's actually the last process that we need to work with, and we'll be done with all separating and purifying techniques. Make sense?
Yes, sir.
So we are left with three processes, and I'm thinking to